Hello everyone. Today we're going to be learning about the mirror equation, sometimes also known as the thin lens equation, as well as other names. But today we're just using it to analyze mirrors, so we'll call it the mirror equation. In this image below, you can see a person holding a mirror in one hand, and in the other hand they have a piece of paper and they're able to project an upside down image of what their window looks like onto the page. But what about the equation? Here's the mirror equation, again, also sometimes used for lenses and called the thin lens equation. And today we're going to learn how to use this equation to solve physics problems that involve mirrors. Before we get started, we should summarize ray tracing, which is a strategy for figuring out where images will be located based on where the mirror and the object are. As a refresher for this image, here's the mirror, which is kind of the obvious part. The image is what's being projected onto the piece of paper, and the object is whatever's providing the light to produce the image. Now, since there are many different types of images that a mirror can produce, let's quickly review the two types of spherical mirrors, concave and convex. A concave mirror is one that is bulged inward, and this is the type of mirror that can create an image by converging light together. Here's an example of what this would look like in the real world. You can see two students who are creating a real image using a concave mirror, and real means it's actually in the room. You could interrupt that light by putting your hand through it. The light is really existent, it's really there. And this is similar to a lab you'll do in this class. For a convex mirror, this is the type of mirror that bulges outward, and instead of converging light together, this type of mirror diverges light, which means it spreads it apart. All of the observers who look at this mirror would think that they're seeing light coming from inside the mirror because of the nature of reflection. Again, this is a review, so I'm expecting you've already seen a little bit about this in a previous lesson. Here's an example of what this would look like on a convex mirror. The thing to note on a convex mirror is that everything seems a little bit smaller than it looks in the real world, and that's because everything is squished down so that you can see multiple perspectives. So now that we've reviewed the two types of mirrors, let's remind ourselves how ray tracing could be used to locate images on these two types of mirrors. Ray tracing is pretty useful. It's not necessarily what this lesson is about, but it's still worthwhile to remind ourselves how it works. Again, this is assuming this is the second or third time you're learning about it. So for a concave mirror or for a convex mirror, you can start out by drawing two or maybe three rays. In this case, I'm just going to do two. And you start with an object, and then you draw two rays of light going from the tip of the object to the mirror. And I'm not really drawing these concave or convex mirrors particularly bulgy or rounded. I'm drawing them as pretty flat because that's what we have to assume that they are in order to get really accurate and precise measurements. If they're super curved, we can actually get problems where light doesn't focus the way it really should. We'll talk more about that in a future lesson. So for the first step, you simply draw these two rays of light, one going parallel to the principal axis and hitting the mirror, and the other going towards the focus point. For the concave mirror on the left, the focus point is in real space, so the light can actually go through that point. But for a convex mirror, that has a virtual focus point, so the light can't actually reach the focus point, but it's still trying to get there. Either way, you've drawn the same two rays. Moving ahead to step 2, the next thing you're supposed to do when you are ray tracing is figure out where those rays of light will go after they've touched the mirror. And of course, they'll bounce off and go back where they came from, but not necessarily exactly where they came from. They might head off at different angles. So for a concave mirror, our rule is that the ray of light that is parallel to the principal axis will bend into the focal point, and then the ray that goes into the focal point will come out parallel to the principal axis. So these two rays are kind of opposites of each other. The same is true for the convex mirror on the right, except instead of converging together, these rays are diverging apart. And it's kind of the same thing as in the concave mirror. On the convex mirror on the right, there's a ray that is parallel to the principal axis, and instead of bouncing towards the focus point, that ray actually goes directly away from the focus point. So it's still doing something related to the focus point, just kind of opposite. And then the same thing with the second ray. The second ray of light is going towards the focus point, just like it did for the concave mirror, but this one is never actually able to reach the focus point, and so it just bounces away parallel to the principal axis kind of early. It does that before it actually ever reaches the focus point because it never quite gets there. So again, we're doing the same thing in both types of mirrors, but the result is different because the curvature of the mirror is different. Moving on to step 3, you look for the place where the rays of light meet back up, which in the case of the concave mirror on the left is that little green dot. That's a location where the rays that originated from the tip of the arrow have now met back up. So an image will be located somewhere around there. For the convex mirror, because those red rays of light, which were reflected off the mirror, because they are diverging and they'll never meet back up, therefore, we'll never actually see them touch ever again, that means you're not going to find any area in real space where an image is formed. So instead, you can trace back with these dotted lines behind the mirror to show where an image would seem to be located. So there would be a virtual image at that location of intersection with those virtual rays of light. So a person could look into that convex mirror and think they're seeing an image, but they couldn't actually reach out their hand and touch it. So the fourth and final step is simply to draw an image, which in the case of drawing an arrow as your object, you would also draw an arrow as your image. And if you have an image that has ended up below the principal axis, as we do on the left for the concave mirror, you would draw it upside down. And if it ends up above the principal axis, like it does for the convex mirror, then you will draw it right side up. So that's a quick summary of ray tracing, and you'll get much better and more comfortable with that as time goes on. So now that we've reviewed that, let's take a look at the mirror equation and see how this can be a useful tool for a different method of finding where an image will be located, what it will look like. You're eventually going to get to choose which type of method you want. You can use sketching or ray tracing, or you can use this new method called the mirror equation. Sometimes you might be required to even do both, just to confirm that you got the answer right. So here we have the basic core elements of a mirror problem. You have an object, which is right side up, and then I'm already kind of showing you the image, and I'm also showing the mirror on the right. Looks like it's a concave mirror. There's a focal point at some distance in front of the mirror, and then I've also added a vertical black line to illustrate the fact that all the rays of light are going to change direction or bounce or reflect at that vertical line. So we're going to kind of ignore the fact that the rays that hit the top and bottom of the mirror technically would bounce away first because the top and bottom of the mirror are closer due to the curvature of the mirror. We have to kind of ignore that and instead just pretend all the rays of light move at that vertical line and change what they're doing at that line. That just makes our calculations more correct and more precise. Okay, so the mirror equation is down below. Let's talk about what these things are. F is a variable that means the distance from the mirror to the mirror's focal point. Sometimes we call this the focal length of the mirror. There's a lab we'll do in this class where you will use experimentation to determine what the focal length of a concave mirror like this is. So that's something you can find experimentally. DO is the distance from the mirror to the object, and DI is the distance from the mirror to the image. You'll notice that all three of these are distances, so all of them would be measured in the same unit. Perhaps they would all be in meters, or they'd all be in centimeters. As long as they're all the same unit, you don't have to do any funky conversions. And you'll also notice that all three of these distances are referencing the mirror. So that makes the mirror the most important item in this whole process. The object and the image, yeah, those are important, but without the mirror, we wouldn't even be doing this physics problem. So the mirror is the most important thing, and that's why all distances reference the mirror. So that's technically all we need to understand the mirror equation, but there's a second equation that kind of goes along with it more often than not, and it relates to the heights of the object and the image. Because as you've probably noticed by now, sometimes the image is not the same size as the object. Sometimes it's really small, sometimes it's really big. It depends on the situation. And so HO means height of the object, and HI means height of the image. And actually, all five of these variables could be positive or negative, and you'll get used to eventually what the negatives mean. But first, what equation do these heights fit into? Well, they fit into something called the magnification equation. You probably are familiar with what the word magnify means. Usually when people say magnify, it means to make something larger. Maybe you're holding a magnifying glass over something to make text easier to read, for example. In this case, capital M is a variable that means magnification. It means how much bigger or smaller does our mirror produce images? Does our mirror produce something that's much, much larger, in which case M would be a large value? Or is our mirror producing something that's much, much smaller, in which case M would be a very small value, something less than 1? M can be calculated with two different ratios, meaning there's two possible methods you can use to solve for M. You can either solve for M using the ratio of the height of the image, HI, to the height of the object, HO, so HI over HO equals capital M. Or alternatively, your second option is you can calculate M using negative DI over DO, which are variables we already defined in the previous equation. Distance to the image divided by distance to the object. And the negative sign there is meant to make everything work out in terms of positives and negatives. Again, you will have practice with that. Not really worth going into the deep explanations now yet as to what the negatives are all about. We'll get there. So let's use these equations, let's solve some problems, and let's see how to apply them. Here's a situation where I've already got the object, image, and mirror, and focal point, and all the normal stuff located. I'm going to point out what the important measurements are, and then we'll talk about what this first physics problem is. There's going to be 2 problems. We'll do the first one, we'll talk about how it went, and then we'll do a second one and we'll wrap up. Okay, so first thing I'm going to point out is that the object is upright and it has some height to it. So this candle could, I don't know, maybe be a few inches tall or maybe like a quarter of a meter. We haven't really defined what that measurement is, but it has some height. And then the image is located upside down and it has a larger height. So I'm guessing that's going to be perhaps like a negative larger number. So if the height of the object is 2, maybe the height of the image will be negative 3 or something like that. Okay, so other things to define. The 3 distances that are in the mirror equation, we could put those in the diagram. DO is the distance from the mirror to the object. F is the distance from the mirror to the focal point of the mirror. DI is the distance from the mirror to the image, which is that upside down image that we are projecting onto a screen. If you're wondering what that kind of square looking thing is, that's like a piece of paper or a piece of cardboard, and we are projecting light onto that screen and making a nice, crisp, clear image of that candle upside down. And if we moved that paper forward or backward along the principal axis, that image would get blurry. So there really is one special spot where we can project that and have it be a nice clear image. So we might need to figure out what that distance is. So here we go. Here's the first of 2 problems. A 3 centimeter tall candle flame sits 8 centimeters away from a concave mirror. And that concave mirror has a focal length of 5 centimeters. So we're being given 3 measurements. They're all in centimeters, so it seems like those are the 3 green variables, the 3 distances. And the first part of this question is, how far from the mirror can an image be formed? So how far from the mirror can an image be formed? So they're really asking, when an image is formed nice and crisp and clear, what will be the distance between the mirror and the image? So they're asking for DI. The part B, and there's going to be ABC here, part B asks, what is the magnification of the mirror? Okay, so once we've determined where the image is or where it's located, then we can probably figure out magnification, which was in the second formula we learned, that was capital M. And the third part of this question asks, how tall will the image be? What will be the height of the image? So let's just start with A, how far from the mirror will the image be? That's going to be DI, which is that bottom green variable, the distance between the mirror and the image. So let's pull out the mirror equation. The mirror equation says 1 over F equals 1 over DO plus 1 over DI. And I haven't really talked yet about how weird this equation looks in terms of its format. We're used to equations that are like something equals something times something, or something equals something divided by something. So compared to our normal equations, quote unquote, this one looks pretty weird. And there's reasons for that, but we don't need to get into them today. So let's just solve for DI. We know that's our mission, right? So let's get DI by itself. DI is all the way on the right there underneath a 1. It's in a denominator. So we're going to have to do some algebra magic here to make this work. First thing I'll do to get DI by itself is get rid of the term in the middle of the equation, 1 over DO. I'm going to shift that over to the left by subtracting it from both sides. I'm keeping my equal sign in the same place so you can have that as a constant there. Okay, so now the left side of my equation says 1 over F minus 1 over DO equals 1 over DI. I've got to do a funky little trick here, a little bit of algebra magic, to solve for DI on the right, because I haven't actually solved for it yet. I've solved for 1 over DI, but 1 over DI is not the same thing as DI. That's kind of like how 1 over 2 is not the same thing as 2. Those are actually different numbers. 1 over 2 is equal to 0.5, which is very different from 2. So I've got to sort of flip or invert the right side of the equation. And actually, that's exactly what I'm going to do. I'm going to flip it on its head. I'm going to put the denominator in the numerator and the numerator in the denominator. So when I flip the right side of the equation, I'll get DI. And that actually means I have to flip the other side of the equation as well, which is going to look really messy, but it is accurate. Instead of having 1 over F minus 1 over DO, I now have 1 over F minus 1 over DO. So I've taken the whole left side of the equation and stuck it in a denominator. Is that pretty to look at? No. But is it correct? And will it get you the right answers? Yes. So I'm just going to start plugging in my numbers now. What were the numbers I needed to plug in? I needed F. And looking back to my problem, I can see that the focal length of this mirror is 5 centimeters. And I can see that the distance to the object, which is the candle, would be 8 centimeters. Plugging those in and crunching the numbers in our calculators, we get 13.33 centimeters, which is the answer to part A. How far from the mirror can an image be formed? In other words, what is DI? The distance DI is equal to 13.33 centimeters. Okay, so that was part A. Let's move on to part B. What is the magnification of the mirror? Magnification, okay, so that was in this equation. Magnification is capital M, so we need to solve for that. So we've got a choice. Do we use HI over HO? I'm looking up at the problem, and it seems like we didn't actually receive either of those variables. They didn't give us those, so we can't use that. So we're going to have to use a version of the equation that just says m equals negative di over do, because we actually do have both of those things now that we've solved part A. Let's plug those numbers in, shall we? di in the previous part we just solved for was 13.33. do was 8. And there's a negative sign in the equation too, so don't lose that. And apparently the magnification of this mirror currently is negative 1.67. So what does that mean? And is there supposed to be a unit on this? Well, I was a little bit lazy and I didn't put my units in the work that I was doing, but I just divided a distance in centimeters by another distance in centimeters. So the units cancel out, so no, there's no unit that's supposed to be there. Magnification is a unitless quantity in the world of physics. So whenever you're calculating magnification, no unit is necessary. And what does the negative mean? Well, the image got flipped upside down, so there's the meaning of negative. A negative magnification means your mirror is going to be flipping images. And the 1.67, well, that's a number that is greater than 1, and so that tells me that my images are going to be larger than my objects. If I got a number less than 1, that would mean I'm shrinking my image. Okay, so now let's solve part C. How tall will the image be? How tall? Okay, so that's going to be the variable hi. Hi is in the magnification equation. And let's see, I think I'll use this version of the magnification equation. You only have to use 2 out of the 3 parts because all 3 parts are equal to each other, so you get to choose what you use here. I do know what the magnification is of this mirror. We just solved for it. It's negative 1.67. And I actually also know what the height of the object is. They said it's a 3 centimeter tall candle flame. I think earlier I might have said they didn't give us either height. That was incorrect. They did give us the height of the object. So I have 2 things. That means I can solve for the third. First, though, I have to solve for the variable I'm after here. I'm after how tall will the image be, otherwise known as hi. So I'm going to rearrange the equation to solve for hi by multiplying by ho on both sides. That makes the equation look like this. Now let's plug in the numbers. I already know that the magnification of my mirror in this case is negative 1.67. I know the height of the candle or the object is 3 centimeters. So 3 centimeters times that magnification factor means the height of my image will be negative 5 centimeters. So 2 things we should notice. The original candle had a height of 3. This image has a height of 5. So that kind of matches our expectation that it's going to get larger because the magnification was greater than 1. And the other thing to notice is that the height comes out as negative, which again confirms our idea about negative heights, meaning that it's flipped upside down. All right, that was the first of 2 problems. The second one is no harder than the first one. It's just an extra opportunity for you to practice. So I know the second one should seem a little bit more approachable. This might have seemed overwhelming the first time you did it. Especially on the left where we do all that flipping upside down. That's a trick that I can actually make a little bit easier for you by giving you a trick to do on your calculator. So pull out your calculator. You can pause the video if you need to, because I'm going to teach you about a special button that can make inverting numbers and parts of equations a little bit easier. If you want to invert numbers, and that means take a denominator and put it in a numerator, and take the numerator and put it in the denominator, like flip something on its head, then you want to use something that I like to refer to as the Flippy Button, which is absolutely not what the button is called, but I love to call it that because it flips things, so it's the Flippy Button. This is the Flippy Button. It is x to the power of negative 1, and what this button does when you press it is it flips whatever number you have just pressed beforehand. So if you type 5 into your calculator, and then you raise that 5 to the power of negative 1 by hitting the Flippy button, and then you hit enter, then it will return a value that is equal to 1 over 5. So by taking 5 and hitting the Flippy button, you got the flipped version of 5, or 1 over 5. If you flip the number 100, you get 1 over 100. So the Flippy button can be used to flip single numbers, or it can be used to flip entire operations. So if I did 2 plus 2, and I'm like, wait, I'm going to want the flipped version of that, I don't have to do 2 plus 2 and then hit enter and then flip it. I can just put 2 plus 2 in parentheses and then hit the Flippy button, then hit enter, and I can kill 2 birds with 1 stone and get a returned value of 1 over 4. So that's the Flippy button. I highly recommend you use it when you're using the mirror equation. So let's see if you can now use your calculator to kind of follow along with the math that I'm doing. In this problem, we can see some creepy looking eyeballs. This is going to be a realistic example of what it's like to use a makeup mirror, which makeup mirrors, if you've ever applied makeup before and used one of those little circular mirrors that you can hold in your hand and kind of see yourself as larger in the mirror. So why does your face appear really big in a makeup mirror? Here we go. First thing I'll mention in this diagram is that when you use a makeup mirror, your real eye has a certain size to it. So we're going to say the height of the eyeball in this case is HO. And then your eye, or whatever part of your face you're looking at, will appear larger in the makeup mirror. We'll call the size of that HI. And then here are the three distances. Now, this is going to be a virtual image, and you can tell that because the image appears in mirror world, kind of on the opposite side of the concave mirror. So when you're looking in a curved makeup mirror like this, you can't actually reach out and touch that larger version of you if you're not really in the mirror. So that's a virtual image. And so that means the distance to the image is going to be on the opposite side of the mirror because the image is also on the opposite side of the mirror. So that's why the DI in this case is not on the same side as the other distances. Okay, here's the problem. A woman's eye is 30 millimeters tall. She holds a makeup mirror 50 millimeters away from her face. The mirror has a focal distance or focal length of 100 millimeters. So just right off the bat, reading that problem with no context, it doesn't really seem like there's a big difference between the 30, the 50, and the 100 because they're just a bunch of things that are all measured in millimeters. So the first mission sometimes is just to figure out what those three things are. So the woman's eye is 30 millimeters tall. That is HO. That's the height of the object. The makeup mirror is 50 millimeters away from her face. That would be DO, the distance from the mirror to the object. And the mirror has a focal distance or focal length of 100 millimeters. So that is the distance labeled F. F is 100 millimeters. So if you're ever sketching a diagram, it's usually a good idea to put the numbers in the diagram so you don't lose track of what's what. Okay, here are the three parts of the question. Part A asks, where will the image of her eyeball appear? Now, it's going to appear behind the mirror. I'm kind of giving you that clue in the diagram. But how far back behind the mirror will it appear to be? Is it going to seem like it's, a whole foot away, or is it going to seem like it's really close to the mirror? Part B asks, what is the magnification of the mirror? And you can probably estimate here or guess that the magnification will be greater than 1 because the eyeball is appearing larger than the object does. And it's probably going to be a positive magnification rather than negative because this mirror is not flipping the eyeball upside down. And then part C, how tall will her eye appear to be? And that's a pretty important question because if a makeup mirror doesn't make you look larger, then it's not going to work as a makeup mirror. So the size of the images that we get is crucial for making a good makeup mirror. So here's the equation. We know we're going to use this at some point, so let's just get it on the page. And let's look at part A. Part A asks, where will the image of the eyeball appear? And that means how far back behind the mirror, so that's referring to DI. Just like last time, let's solve for DI by getting DI by itself in the mirror equation. We'll move DO, or rather we'll move 1 over DO to the other side of the equation by subtracting it away. So now the left side looks like 1 over F minus 1 over DO equals 1 over DI. So let's now flip both sides of this formula. Let's flip the left side and put it all in a denominator. And let's flip the right side and take that DI out of a denominator and put it in the numerator. So now we've just taken the whole equation and flipped it on its head. And that's an okay algebra move to do because you did the same thing to both sides. As long as that happens, you can do pretty much anything you want when it comes to algebra. Okay, so now let's plug our numbers in. What was F? F is the focal length of the mirror, and in the problem they say the mirror has a focal distance of 100 millimeters. So let's plug in 100, and then we're plugging in DO, the distance between the mirror and the object, which is the eyeball, and they say she holds a makeup mirror 50 millimeters from her face, so 50 is what we plug in there. When you crunch all these numbers, and if you want, you can pause the video now and see if you can get this answer by using the Flippy button. I'll let you pause now and try it out. Okay, if you did it correctly, and by correctly I mean typing into your calculator 100 Flippy button minus 50 Flippy button, and then Flippy button again on that answer. There were 3 flips there, and that's why having the Flippy button can really be an advantage here time-wise. That's how you would get that answer of negative 100 millimeters. So did we just get an answer? Yes, we did. The distance to the image of the eyeball in the mirror is going to be a distance of negative 100 millimeters. So here's something weird. We have a distance of negative 100. So what does a negative distance mean? A negative distance means you are going a distance into the mirror world. It means you're going in some distance into a land where there really is no light. And that's the significance of a negative on a distance. So that was part A. Part B asks, what is the magnification of this mirror? So the magnification of the mirror, that's capital M. I don't see that in the diagram. That's because it's not usually drawn into diagrams. M is more like an idea of what the mirror is accomplishing. So capital M, or magnification, is equal to one of two things. We can either say it's HI over HO, or we can say it's negative DI over DO. HI over HO, well, we don't have HI yet, so we can't use that. So let's use the version that looks like this. Magnification equals negative DI over DO. We do know what DI is, we do know what DO is, and we know what negative is. It's just a negative sign. So let's just plug all that stuff in. Magnification equals negative 100, so there's a double negative, literally, so that will cancel out to a positive number. And 100 divided by 50 is 2. So the magnification of this mirror is positive 2. And the positive makes sense because we didn't flip the eyeball upside down. And 2 makes sense because that's greater than 1, so it means our image got larger. And in fact, this means it got larger by a factor of 2, so it's twice as big. That image of the eyeball is twice the size of the real eyeball. So now the last part. How tall will her eyeball appear to be when she looks at it in the mirror? So we could kind of figure this out by just saying, oh, her eye is 30 millimeters tall, and it's magnifying it to be twice as big, so 2 times 30 is 60 millimeters, and that actually is the answer. But let's do it the real way by showing our equation to show why we know that's the answer. So this version of the magnification equation is what I'm going to use because I know the magnification of the mirror. The height of the image is what I'm after, and the height of the object is also known to me. I know what that is from the problem. Rearranging to solve for the thing I don't know, which is HI. My equation looks like this. Magnification times height of the object equals height of the image. Magnification, we just learned, is 2. The height of the object is 30 millimeters. That's how tall her eyeball really is. And that means the height of the image will be 2 times 30, or 60 millimeters. Phew! Pretty fun, huh? That is some tough algebra. It's some of the toughest algebra we'll do all year. But use the Flippy button to your advantage. Again, you can go back and rewatch the parts of the video where I crunched the numbers at the end of using the mirror equation. That's the green equation. And that was when I would use the Flippy button 3 times in a row to flip minus flip and then flip one more time. And if you can get good at that, then this will be a breeze to you very quickly. So good luck in your physics work, and I'll see you in the next video.